Hi, how you doing today? We're going to talk a little bit about similar solids. So this is going to be our last section in our 3D shapes unit that we're doing. And so I want to look at what happens when we have similar figures that are three-dimensional today. And really what I want to look at for the most part is what happens in terms of ratios of the pieces. And so we've talked about similar figures before and set up proportions and ratios and solve those. We're going to do a little of that, but we're going to see there's a little difference with just the side lengths and the ratios of areas and ratios of volumes. So first off, what it takes for solids to be similar. This is solids where all the lengths that line up are in the same ratio. And so I've got a set here that are similar figures because you notice the 4 goes with 8, the 2 goes with 4, the 3 goes with 6. Every single ratio here would simplify to 1 to 2. Everything there is half the size that it is here, or everything here is twice the size that it is there. So the ratios are all exactly the same. Now, the ratio of sides is 1 to 2. Let's see if we can find the ratio of areas and the ratio of volumes to see if that fits that exact same scale factor. So let's do surface areas first. So surface area, I put the formula up here. This is a good reminder of how to do some of this stuff. So surface area is 2 times the area of the base plus perimeter of the base times the height. And so the area of the base here, the base is a rectangle that's 4 by 2, so the area of the base would be 8. And so plugging this stuff in here, I have 2 times 8 plus perimeter of base would be 4 plus 2 plus 4 plus 2. So we've got 8, 9, 10, 11, 12. So we've got 12 for the perimeter of the base, and then the height would be 3. So in other words here, we've got 16 for that part plus 36 for this part. And so that's going to make our surface area on this one come out to 52. So there's our surface area there. Now let's find the surface area on our bigger one over here. So same exact formula, because it's still the same shape, a rectangular prism. 2 times the area of the base. Area of the base on this one is 8 by 4, so the area of the base is 32. Perimeter of the base on this one is 8 plus 4 plus another 8 plus 4, so that's 12, and then another 12, that's 24 for the perimeter of the base, times the height, which in this case is 6. All right, so this is going to give us 64 for this part, plus 24 times 6, which gives us 144 for that part. And if I add those two together, that's going to give me 208. All right, so our surface areas are 52 and 208. We're going to use those numbers in just a second. Let's go ahead and find the volumes as well. Volume is area of the base times the height. So area of the base here is 8. Height is 3, so that's 24. All right, let's do the same thing here. Volume is area of the base times the height. Area of the base here is 8 times 4, that's 32. Height is 6, so we've got 32 times 6 for the area of this one, which gives us, or the volume of this one, so that gives us 192. All right, now let's make some fractions here out of this and see what conclusions we can come to here. So the ratio of the sides, we already said was 1 to 2. Let's talk about the ratio of surface areas. Well, we got 52 for the smaller surface area, 208 for the bigger surface area. Now, if I divide both of these by 52, 52 actually goes into both of these. 52 divided by 52 is 1. 208 divided by 52 gives us 4. So the ratio of areas is 1 to 4. All right, the ratio of volumes is, we got 24 for the small volume, we got 192 for the big volume. 24 divided by 192, if I divide both of those by 24, 24 divided by 24 is 1. 192 divided by 24 is 8. Now, here's what I want you to notice. The ratios all came out different. Now, the reason for this, we talked about similar things being in the same ratio. That is still true for lengths. All the lengths will be in the same ratio. So every single length in here would be in the ratio of 1 to 2. However, areas are not lengths. Areas are two-dimensional, right? We have length and width, in this case, if it's a rectangle, to get area. Since area is square units, two-dimensional, what we actually have to do with these numbers is square both of them. Now, the 1 didn't change because 1 squared is still 1, but 2 squared is 4. And so because we use square units, because area is two-dimensional, we use square units, we square both of the numbers in that ratio. Now, if you're noticing the pattern there, for volume, when we measure volume, volume is three-dimensional, right? And we use cubic units. And so what we do with our original ratio is we cube both the numbers. We multiply them by themselves 3 times. So 1 cubed, or 1 times 1 times 1, is still 1. 2 cubed, 2 times 2 times 2, is 8. So that's the ratio of the volumes. So let's see if we can generalize what happens up here. So if the ratio of sides is some number A to some number B, that means the ratio of the surface areas. Area is two-dimensional. We use square units, so we square that ratio. That's A squared over B squared. So square both of those numbers in that ratio, that's the ratio of the surface areas. Ratio of volumes, volume is three-dimensional. We use cubic units, so we cube both of the numbers in that ratio of lengths. And so this is going to be A to the third power, A cubed, over B cubed. And so there's our general formula. And so this kind of is at the heart of everything else we're going to do today, is that summary right there. Whatever the ratio of sides is, that's the ratio of any lengths. If we're talking areas, we have to square both of those numbers in that ratio. If we're talking volumes, we have to cube both of the numbers in that ratio. So let's see if we can put this to use on a couple examples then. So let's see if I have this first one here. I've got a couple cones, and I left out some information on purpose because I don't want you to have to try to find the volumes and surface areas to do this, because you don't need to know them. All you need to know is the ratio. And so we could find the surface area and volume of this cone because we know the radius and we know the height. And so we could get the slant height if we needed to, and we could find the surface area and we could find the volume. This one, we don't have enough information. It's impossible for us to find the volume of that just having this information right here. And that's okay, because we don't need it, because do you notice what this says? It doesn't say find the actual volume or find the actual surface area. It says find the ratio. So we're going to find the ratio of the lengths, the ratio of the areas, the ratio of the volumes for these two cones. So the ratio of the lengths. Well, let's find a set of lengths where we know both of them here, which would be the 12 and the 8. We know the height of both of these. And so since it doesn't give a certain order, you could actually say 12 to 8 or 8 to 12. Either way would be fine. If it said, go from this shape to this shape, you'd want to put it in a certain order. And so I'm going to go 12 to 8, just kind of reading left to right. Now, don't leave your answer like that because it's not simplified. Let's think about what number goes into 12 and 8. 4 would go into both, right? So 4 times 3 is 12, 4 times 2 is 8, which means that ratio of lengths is 3 to 2. That's actually going to make your life easier for these next two if we simplify that at the beginning as well. So that's 3 to 2. Now think about what we just found out a minute ago. If I want ratio of areas, the thing that I do to both of these numbers in that ratio, area is two-dimensional, so I square both of them. So this is 3 squared over 2 squared would be that ratio. And 3 squared is 9, 2 squared is 4, so the ratio of surface areas would be 9 to 4. Now remember, we're not trying to find the actual surface area, we're just saying what is the ratio, that is the ratio. And then the ratio of volumes. Volume is three-dimensional, measured in cubic units, so we cube this ratio that we have here. So I'm going to cube the 3 and the 2, and 3 cubed, 3 times 3 is 9, times another 3 is 27. 2 cubed, 2 times 2 is 4, times another 2 is 8. So the ratio of volumes would be 27 to 8. All right, so there's how we find the ratio of lengths, areas, volumes. Square it for the areas, cube it for the volumes, and that's our ratios. Now let's put this to use because this one is just kind of practice on how we get those. In a practical example, it might look a little bit more something like this. So if I have two cylinders in this case that are similar, so larger similar cylinders, so we know they're similar, and I know the volume of this smaller cylinder is 81 cubic inches, or cubic centimeters, sorry. And I want to know what's the volume of this bigger cylinder that's a similar cylinder. So we're going to do some proportion work here. Very common mistake on one of these is just set up a proportion and go for it and do something like 14 over 81 equals 32 over x, cross multiply, solve the thing. That's not going to work because 14 to 32 is the ratio of lengths. We need the ratio of volumes. So we're going to have to do a little work here to get the ratio of volumes first, then do the proportion. So the ratio of sides here. Sides is 14 over 32. If I go like smaller to bigger, the one on the left to the one on the right. Now I'm going to simplify that just to make my life easier. You would actually get the right answer if you didn't simplify it. It just is going to have to deal with much larger numbers if we don't simplify. So let's think about what number goes into 14 and 32. All right, 2 goes into both of those for sure, right? So 2 times 7 is 14. 2 times 16 is 32. So the ratio of the sides is 7 to 16. Now I picked numbers that don't work out all that nicely on this one on purpose because real life stuff doesn't always work out with things like 1/2 and things that easy. Now let's think about this. What does that make the ratio of volumes? To find the ratio of volumes, we said we need to take that ratio of lengths or sides and cube both of those. So I'm going to cube 7 and I'm going to cube 16. So 7 cubed is 343. So that's our top number. 16 cubed is going to be a fairly large number. 16 cubed is 4,096. This is the ratio that relates the volume of this shape to the volume of this shape. That means this is what I need to use when I set up this proportion. So the ratio of volume of this to this is 343 to 4,096. So 343 to 4,096 is the ratio of the volume of this smaller one to the volume of the bigger one. Now think about how we want to set up this proportion. We're going small shape to big shape. We want to go small shape to big shape here. There our volume's 81. Here our volume is unknown. I'm just going to call it x. And so our 81 is the small shape. Our x is the big shape. So we want our proportion to look like that would work. That's not the only correct setup for this, but that is a correct setup that would work. And so when I cross multiply here, I'm going to have something like 343x equals 4,096 times 81, which is going to be an even bigger number, 331,776. Now to get x completely by itself then, we just need to divide both sides by 343. All right, so if I do that, that gives me the volume of the larger shape here. The larger cylinder is 967.28, and that would be in cubic centimeters. All right, and just a side note on this, there's another notation for cubic centimeters that you guys might have heard before, cc's. That's another notation for cubic centimeters. That's used in medicine when they give cc's. That's also used in engines, like dirt bike engines, like a 125 is 125 cubic centimeters is the displacement of the cylinder inside of that engine. That's why it's called 125 cc. Bigger displacement means more power because there's more room for gas to explode and make the cylinder, make the piston move up and down in the cylinder, which gives you more power. So that's kind of how this works as far as using these. The big takeaway from this is whenever you have ratio of lengths, you need to square that ratio to get ratio of areas. You need to cube that ratio to get ratio of volumes. That's really at the heart of this whole thing.